Okay, and that leaves us to our third perspective, which will be Dr. Stuart Parkin, who is IBM Fellow and the Director of the IBM Stanford Spintronics Center, and of course is famous for many important pieces of work, including magnetic thin films and spintronics and much more besides. Oh, I've learned how to do that.
Thank you. Okay, well, good afternoon. I'm very pleased to be part of this celebration, and I've seen the London Centre evolve over the last 8 years and to become the very impressive Centre for Nanotechnology that it is today. Well, I was asked to make a few comments on the perspective from the information technology industry of nanotechnology, so I want to make a few comments. If I can get to the next slide. So first, I wanted to look at how the computing industry has evolved over the last 20 years. And I've taken this figure from a very interesting paper in Science that was published earlier this year. And this basically discusses how the world's compute and storage capacity has evolved. So this foil shows you that in 1986, 41% of the world's computing capacity was used for pocket calculators. And today, only 20 years later, then rather than pocket calculators, the world's computing capacity largely is dedicated to personal computers and increasingly video game consoles. So I'm not sure what that means, but from an IBM perspective, then our main interest is in the most largest types of computers, server computers, and you can see that's a relatively small percentage of the computing capacity today. The other point I wanted to make, of course, as we all know, is it's extraordinary how the evolution of computers and storage technologies has evolved so rapidly and exponentially over the last 4 decades. This only shows you the last 2 decades, and you can see then the world's computing capacity has increased by about 4 orders of magnitude. Now let's look Let's now look at the storage capacity. And again, I've also borrowed this figure from the same paper in Science. And well, the biggest change here in the last 20 years is the change from storage of data in analog forms to the storage of data in digital forms. And if you look at the orange colors here, show you basically analog means of storage, and the blue shows you digital means of storage. And today, most data is stored digitally, and a lot of that data, in other words, the largest segment, is stored in magnetic disk drives. And although magnetic disk drives have been around also for 50 years, invented actually by IBM, their storage capacities have increased also exponentially or super exponentially over the last several decades. Now, an important point, though, is in this foil is that although it only shows you here that the storage capacity, the world's storage capacity, has increased by 2 orders of magnitude in the last 20 years, the storage capacity for digital data is actually increasing at a much faster rate. As you can see, since the year 2000, when only a few percent, 5% of the world's data was stored in magnetic disk drives, and today it's 42% of course, a much larger volume of data. Okay, these are a couple of points I wanted to make. Another point I wanted to make is that these technologies are evolving so quickly that it's often very difficult to remember that it was only a few years ago that we didn't have access to data in the way that we have it today. So it wasn't possible even 8 years ago to do Google searches, for example. And so the world has really changed, and it's changed in ways that are extraordinarily rapid, but in ways that people readily accept. So it's impossible in a few moments to discuss all the trends in nanotechnology for this industry, which is, of course, a multi-trillion-dollar industry today. And one important change that I'm going to briefly discuss is a change from a world of IT, which is centered on computers and computing, to a world centered on data. And what does this mean? This means that there is a real data explosion, vast increases in the most useful types of data, digital data, data that we can analyze, apply analytics to, and therefore extract enormous value. So these enormous amounts of data are also largely what we call unstructured. They're not in databases, but the most interesting data today is in all sorts of other forms, which is much more difficult to analyze. And also there's a huge increase in what we might call big data, data bases, which is so enormous that it's difficult even to store those data, and it requires real-time analysis of that data. In other words, we're throwing a lot of useful information away. So what do we need? We need new means of storing data. I'm going to come back to that in a moment. Now, another very important trend is that we're coming to the end of the silicon age, if you like, and already this afternoon you've seen Moore's law mentioned and displayed a couple of times, so I'm not going to show that. But Moore's law has been the evolution over 4 decades of the silicon-based transistors. And today we've reached the end of that scaling. In fact, it was reached approximately 8 years ago when the fundamental frequency of operation of these transistors stopped scaling as it should according to Moore's law. And this was because of the energy consumed by these transistors becomes so great that most of the energy is wasted. So basically what we need to do is to develop new types of computing devices that consume vastly less energy. And this will require architectures very different from the von Neumann architectures that we use today. And a very important area here is the notion of cognitive computing and the inspiration we can take from the biological world to enable us perhaps to develop computing devices that can do more, but using vastly less energy. And of course, I'm not going to say anything about quantum computing, but there have been enormous strides in the development of quantum computers, even in the last small numbers of years. So we can anticipate in the next 3 to 5 years the development of real quantum computers using perhaps 100 gates. Now, end of CMOS scaling means that we also need to change the way we architect silicon-based computers from fundamentally two-dimensional architectures. Today, silicon-based computers use a single layer of transistors in the surface of a single crystal of silicon, and we need to move towards what I call innately three-dimensional architectures, such as those in the brain. And we also need to build new functionalities onto chips. These can be devices that sense, many different types of sensors, and other functionalities that are enabled by some of the new fields of nanotechnology, and my own area of particular interest is that of spintronics. If there's time, I'm going to make a couple of comments about spintronics. And then I think a very important point is that many of the major developments in the IT industry over the last 40 or 50 years have been enabled by the development of new materials. And the materials discovery today takes an enormous amount of time. Today, perhaps, we're moving to a new era in which we can accelerate the discovery of new materials using, for example, computational materials discovery. But what's important is clear that the ability to engineer materials on the atomic scale, one atomic layer by one atomic layer, this is possible today, and these materials are used in IT, both in computing and for data storage. We will be developing many new types of what I like to call unnatural materials, materials you cannot find in nature, but which have properties or combination of properties engineered for specific applications. These are incredibly important, and it's possible today using atomic engineering even for mass manufacturing. So let me just come back then to this point that we're undergoing perhaps a fundamental historical transformation in computer architectures from the older compute-centric model to one of the data-centric model as shown in this foil. What does that really mean? It means that today we have a central processing unit, and we move data to that unit from a hierarchy of data storage devices, from high-performance memory, typically static and dynamic random access memories, and the data then is moved off these memories, which are too expensive to store so much data. They're moved to magnetic disk drives, and some of the data is moved further out to tape, which is even cheaper. So today we're moving then to a new model, if you like, in which data will live in persistent memory surrounding the central processing units. In other words, the data itself will be accessible. All of the data will be accessible in new types of memories. Now these new types of memories, we call them storage class memory. I'm not sure if you could see that, but basically we want to eliminate this hierarchy of data storage and develop a single device that will enable us to store cheaply and with high performance all data in one type of device. And this will give rise to huge changes and impact on computing systems. So, I want to briefly then, in the last few moments, discuss how we might develop a storage class memory. So let me just show you here. These are a series of new types of memories that are being developed or have been developed over a period of, in many cases, many years. And these are all non-volatile, in the sense that no power is needed to maintain the memory in these devices. And they basically fall into these three categories. One in which we store a quantity of electrons or dipole moments, such as in ferroelectric random access memory. And in many ways, these memories are the least useful. Secondly, we could store data in the form of resistor devices, and these resistances take several levels corresponding to different memories, if you like. They can be a 0 or a 1. And these are of many different forms today. Almost any material, you can turn it into what you would call a resistive random access memory. And these memories are more useful because you can usually access or read these memories by just simply flowing a current through them for a longer period of time. So this means that they are scalable to extremely tiny dimensions. And then finally, there are memories using the spin of the electron. And I want to briefly discuss one memory of this type. So, if you like, all of the memories I just showed you, I would call conventional, in the sense that each of them uses a memory element which is accessed by a transistor. And the scaling of these types of memories is very similar in all cases, and it depends on the scaling of the transistor or the switch we use to access a particular memory element. So we need to think of memories that we can reduce their cost, and we can only do that by, if we want to base it on a transistor switch, by storing many, many more bits per transistor element. And if we can store 10 or 100 bits per transistor, then we can reduce the cost of these memories to that of, for example, a magnetic disk drive cost, and so we could eliminate the magnetic disk drive and have one type of memory. Now, there are not too many ways in which one can achieve this 10 or 100-fold reduction in cost, or in this way. So, one way to do it is using spintronics. If I might just take a couple of moments to briefly show you how we think we can do this. This cartoon shows you a device that is used today to read information in magnetic disk drives. It's a material that we developed relatively recently, only 10 years ago, and yet it found its way into all magnetic disk drives in the space of 6 or 7 years. This device consists of two magnetic layers separated by a tunnel junction, and the electrons tunnel from one magnetic layer to the other. When the magnetic layers are parallel, the tunneling current is increased compared to the case when these magnetic moments are anti-parallel oriented to each other. The reason is that the current that tunnels is innately polarized. It consists of electrons of one spin orientation, and by nanotechnology means we can develop materials in which the current of electrons is nearly 100% polarized. It consists nearly of electrons all with their spins oriented in the same direction. And this means that when we change the orientation of these magnetic layers from parallel to parallel, we can change the conductance by up to a factor of 10, enabling us to build very high performance memory and sensing devices. So this type of device enables us to sense magnetic fields. The magnetic fields changes the orientation of these two magnetic electrodes, and these, as I said, have been used in magnetic disk drives for about the last 3 or 4 years, enabling these drives to be even cheaper, but at the same time, since a single device is used to read all the data in a single disk drive, today several hundred gigabytes, it's relatively slow, and because it's a mechanical device, rather unreliable. Okay, so we can make a more reliable device by using the same magnetic tunnel junction as a resistive memory element in a simple random access memory, as shown in this cartoon. And the reason I wanted to show this is that this concept we actually proposed 15 years ago. You can't really find this today in the marketplace, but interest in this technology has become of increasing importance in the last year or two, because scaling of silicon devices means that they cannot scale conventional charge-based memory, such as dynamic random access memory, will no longer be useful at a size range of 7 to 10 nanometers. This device will still work. However, at the same time, it's still a conventional in the sense that one of these spintronic resistive elements is accessed by a single transistor. So it's high cost. Rather, we can build a very different type of device, and I don't have time to discuss it in any detail, but we plan to use conventional silicon electronics to manipulate data in the form of these magnetic domains, which you can see here, which are moved around a racetrack consisting of a nanoscopic magnetic nanowire using currents of spin polarized electrons, which will drive these magnetic domains around these racetracks, enabling us to read them and to write them at a single point along the racetrack. And because then we can store about 100 of these domains per access device, we can reduce the cost by 100-fold and increase the capacity of memories by about a factor of 100. Now, this is a prototype device of this type that we built in collaboration with ITRI in Taiwan. But there's no time to discuss. So what to do? How much more time do I have? A couple more minutes? Then I'd like to briefly discuss in this couple of minutes how we might build new types of cognitive computing devices inspired by the brain. And in IBM, we started a program 2 or 3 years ago with substantial funding from the DARPA in the United States to build a memory of this type. So just, I'm sure you're all very familiar with how the brain is structured. Basically, it consists of neurons, the computing elements, if you like, which are connected by these wires and these synapses. And what we want to do in this case is to use silicon elements to replicate the neurons, but use novel types of nanotechnology devices to simulate the synapse. And the most important point in the brain is that the wiring is not fixed as in silicon-based computers, but essentially is plastic and evolves as we use these devices. Now, why are we interested? We're interested because if we look at the computing capacity of mammalian brains, such as a mouse, a rat, and a human, and we compare that to one of the world's most powerful computers made by IBM, this Blue Gene computer, then if you look at these estimates of the computing power, you'll see that, let's say we take the rat. It has a computing power of about 78 teraflops, according to Dharmendra Moda and some of his colleagues at IBM Research. So Dharmendra is in charge of this project. And this same rat has a memory of about 7 terabytes. Now, we compare that to this Blue Gene, which is roughly a 3-year-old machine with 32,000 silicon processors. It has 8 terabytes of memory and a computing power of 90 teraflops. In other words, pretty similar to this rat. But what's... so that's what we think. So a little bit surprising. Now, what's more surprising is if we compare how well does this rat consume, how well does it compare with IBM's computer if we look at energy consumption. So to cut a long story short, this rat brain uses this month 50 milliwatts and our computer 400 kilowatts. And of course, a rat also consumes much less space. Well, this is extraordinary. Quite frankly, we don't know the answer. Why is it that these mammalian brains can carry out so much computation using so little power? But we know that they don't do it in the same way that we compute using silicon-based devices. So we need to essentially architect new computing devices which will operate in a very different way. So I probably don't have time to discuss how we're going to do it, but we're planning, or we are in the process of building chips which will have about 10 billion synapses per square centimeter and about 1 million neurons in the same space. And I forgot to say that one very important distinction from the biological brain compared to silicon is that the computing devices, the neurons, are connected to each other by about 10,000 wires. So the interconnects are totally different. So this is what we plan to do. And, well, I'm probably running out of time, so I won't tell you this. I'm going to say a very important feature of the synapse, as I mentioned, is its plasticity. This is based on something called spike timing dependent plasticity. I'm going to briefly illustrate it, then I'll come to an end. I apologize for going over by a few moments. But the idea here is that when neurons spike and give rise to voltage spikes, these spikes from the neurons that precede and follow a particular synapse will arrive in a particular sequence. And as I just showed you in this cartoon, when the presynaptic neuron spikes before the postsynaptic neuron, that leads to an increase in conduction of the synaptic connection. Whereas when these voltage spikes arrive in the reverse order, within a time period of about 100 milliseconds, then the synapse will weaken. This is called spike timing dependent plasticity, and is shown here. This is basically the change, if you like, of the conductance of the synapse as dependent on the timing or the arrival time of these spikes from the neurons preceding and following a particular synapse. Well, to cut a long story short, we can do essentially the same thing using one of these magnetic tunnel junctions, and the reason is because when current flows through this device, the current of spin polarized electrons carries spin angular momentum and will cause the magnetic moments to change. So since I'm running short, I will just basically show you that using an array of 100 of these tunnel junctions, we can essentially mimic almost exactly the biological synapse in terms of this particular property. So I think I have to come to an end, so I want to just conclude by pointing out that today in IT there's enormous changes taking place in technology because of the end of scaling, both of silicon MOSFETs and magnetic disk drive technology. And we essentially then need to consider all sorts of approaches, but one which will inevitably take place is the concept that we will move from a two-dimensional world to one which is innately three-dimensional. And both this racetrack memory I mentioned is three-dimensional, as of course is the structure of the brain. So I'd just like to conclude. Thank you very much for your attention, and again congratulate Gabe and all his co-workers for the wonderful achievement of building the London Centre for Nanotechnology. Thank you very much.
Thank you very much, Stuart. Plenty of food for thought in that thought. Certainly a few thoughts racing around my brain. We'll finish with our final speaker to draw things to a close is Malcolm Grant, of course, the President and Provost of UCL.
Well, thank you very much. I'd like to say how pleased I am to be here at Imperial. That's what I'd like to say. But of course, Keith, it's absolutely true. And the London Centre for Nanotechnology is a marvellous way of celebrating the collaboration that has occurred over the past 5 years between these two great universities. But I've been very struck listening to those papers at the sheer excitement of the science. I mean, the sheer excitement that Stuart Parkin has just managed to convey to us. And I thought that was very well matched also by Pepper Denman. Thank you very much for those presentations. And just 3 comments on them. First, the sheer interconnectedness of those 2 presentations. The extent to which Stuart and his team and others around the world can develop the ICT, the speed of processing, the capacity for handling data, will in itself empower the development of the medical advances that Pepper was talking about. We are going through yet again a reform of the National Health Service in this country. We have one of the best health services in the world, but it's nowhere near good enough. And we know that there will be a revolution in the next few years as we try to ensure that improvements in diagnostics and pharmacogenetics and in self-care and self-treatment are brought home to patients, giving them, as Pepper described, the capacities to control their own medication and their own choices. But that then brings me to the second question, which is the extraordinary importance of what is sometimes overlooked, but which was touched on in Adrian Smith's presentation, which is the political, and I would say the social science environment in which discovery and new technology is brought into what is sometimes an unreceptive public domain. I had the responsibility some years ago of chairing the government's commission on GM crops, so I know well, through scars all over my back, where the problems lie. Overnight, a whole generation of plant scientists developed a clear-spoken expertise on economics and monopoly power and pricing in global markets for seeds, and equally an entire generation of organic farmers pronounced with great authority on gene flow and upon the incidents that would flow from the uncontrolled growing of GM crops in the open. These were two communities whose voices never overlapped, who never engaged in trying to work out what were the differences that lay between them in the introduction of important technology across the world. The consequence is that Europe still lags behind the rest of the world in the cultivation of GM crops, and there is huge political opposition to them. 4 years ago, both the Royal Society and the Royal Academy of Engineering joined together and produced a working party and a report on nanotechnology, bearing in mind the malign forces that had torn apart the debate on GM crops. We should not forget that report, and we should revisit it from time to time. There has always been a difference in biotechnology between green and red, between agricultural biotechnology and medical biotechnology, to which the public has a much greater affinity. It seemed to me that the examples that we were given today, particularly in relation to medical nanotechnology, are examples which will compel and must be used to drive a positive debate about the potential capacity and empowerment that will come from nanotechnology. My final point is that the politics which Adrian Smith described are nowhere near as dull as he pretended. And I would like publicly to pay our gratitude to Adrian for what he's done in holding the fort for investment in science in this country against a political, how we say, negativity sometimes that's been encountered. The future is not secured, it's not guaranteed, it's not as bright as we might have hoped, but nor is it as devastating as was being widely forecast 2 years ago. Nanotechnology always gives proof to the Vice-Chancellor's dictum of the relationship between the size of what's being studied and its cost. It's inverse in the case of nanotechnology. And I don't believe that all the investment in this country in nanotechnology has been wisely placed. There have been times when it has been scattered across the country. I recall a few years ago when every regional development agency was asked what was its vision for the future, and they replied as one, nanotechnology. It can't work like that. Investment for the future has to be highly focused. We had a brilliant presentation at the meeting this morning from Professor Zhan N. Chan from Beijing, who demonstrated to us the sheer force and potential of investment in science and in nanotechnology in China, the dominant position to date of Japan, and the extent to which China is now catching up on that position. We stand to lose market share and competitiveness in this country if we're not aware of what is happening elsewhere, and we don't recommit ourselves to investing significantly in nanotechnology for all the reasons that have been outlined this afternoon. It falls to me to close the seminar, and to do so by thanking all of those who have given such exciting speeches today, to our sponsors, and to you, Keith, our host, and Imperial College. But finally, to express our congratulations to Gabriel Apley and the whole team of the London Centre for Nanotechnology, and to expect from them a further 5 years of outstanding growth and performance. Thank you very much.
So thank you very much. That brings us to the close of the formal proceedings, and thank you to all the speakers and for all completing such a tight programme on time.